and we got into Newton's laws, and that's kind of been the main theme here. That's what we're focusing on. So, today we're going to finish up Newton's laws. So last class we introduced Newton's first two laws. Not really much logistics today for once. Wild. So we can just jump right into things. So we said we did finish up with circular motion. We said the acceleration is towards the center. Anytime something's going in a circle, the acceleration is always towards the center. This centripetal acceleration. We then went into, okay, what forces. We said a force is a push or a pull. We talked about the fundamental forces. Talked about different types. And then, we got into Newton's law. So the first law says things keep doing what they're doing. That's my definition. It's not the most accurate in wording. The more accurate one is a object at rest stays at rest, or an object in motion stays in motion until acted on by a net force that is not zero. So the example I gave you all was a bullet fired in space will travel forever and ever and ever and ever and ever and ever until it hits something. Or when you're driving your car will stay when you are going 60 miles per hour in cruise control, your net force acting on it is zero. The second you take your foot off the gas, you start to slow down. Not because things naturally slow down, but because of friction and air resistance. And that causes it to slow down. Whereas in space, we don't have those things. All right. We then got into that it is not the weight that determines how difficult or easy it is to move something, but the mass. And we mentioned that kilograms, though we are more commonly used to kilograms being weight, in a physics, a science, a engineering context, kilogram is not weight, it is mass. It is how much stuff something is made up of. How much stuff, it's mass. And so Newton's second law says that the force acting on an object equals the mass of that object, how much stuff it has, times whatever it's accelerated by. Or, honestly, one way that's kind of easier to understand it, the acceleration an object experiences, how much it's speeding up or slowing down. You take the force acting on it, the net force, and you divide that by its mass. This is true in space, just as much as it's true on Earth, just as much as it's true anywhere in the universe. It is very hard to move things that have a lot of stuff. It is easy to move things that don't have much stuff. That's what this equation says. So if you have a giant spaceship way off in space away from all the planets, it weighs nothing. Absolutely nothing. It has zero weight to it, but it would be very hard to move still. A giant spaceship still needs giant engines to move. Not because it weighs a lot, but because it's got a lot of stuff that you're trying to get to move. Okay, and then we did a little bit of playing around with this, and I'll go ahead and write this one a bit better. Got a new battery for my thing, so there, we're all good there. So the last thing we covered was I said object A has half the mass of object B. I want to accelerate object A 4 times as much as object B. How does the force on A compare to the force on B? And so the key to this is the force on B equals the mass of B times the acceleration of B. You know, whatever's going on with B is B, whatever's going on with A is A. So that's, and you know, the force of A equals the mass of A times the acceleration of A. But I want to figure out the relationship between these. Thankfully, I have the relationships between those variables. The mass of A is 1/2 the mass of B, so I can replace that. MA equals 1/2 mass of B. The acceleration of A is going to be 4 times the acceleration of B. And so if I just pull all that to the front, 4 times 1/2 will be 2. And I get mass A, mass B. And long story short, if we compare that, that is 2 times the force of B. Okay? So, something that's a little tricky here, and I'm glad someone mentioned this. One of the things that can be a little bit confusing here is we know that the force of A is going to be twice as much as the force of B. And sometimes we can look at something like this. We can look at something that says FA equals 2FB, And it may be tempting to think that that means that the force of B is twice as much as the force of A, but that is not what that says. And an easy way to prove that, just make up numbers. Just make up numbers. In a problem like this, if you're uncomfortable working with those variables, make up numbers for them. Make the mass of B 1, make the acceleration of B 1, and then we could actually calculate it. So if we just made up some numbers, you're allowed to do that. The force of B would then be 1 newtons. I could then do the exact same thing here. If I want to see what the force is going to be, I can make, so that would be 1/2 times 1 times 4 times 1, and you'll get 2. And we can see then it's twice as big as the other one. So that's one way to do it. And then we can see again here our answer, if FB is 1, FA is 2, oh, it's twice as big. So in problems like this where I say, hey, variables change, how does that affect things? Make up numbers. And the easiest number to work with is 1. Make every variable equal to 1. If one of them doubles, 1 times 2 is 2. If one of them triples, 1 times 3 is 3. If it halves, so on and so forth. So you can mess around with the variables. If that is uncomfortable to you, though, you can just make up numbers. All right, I'm checking. Yep, I was afraid of that. It is doing the ghost thing. So goodbye. So now what we're going to be getting into is we're going to, surprise, surprise, we've done the first 2 of Newton's laws. You can guess what's going to come next. The third Newton's laws. So we'll get into that, but before we do that, I have one question in between that. And that is, so again, just helping us understand forces. Are there forces acting on you right now? You're sitting in your chair. If you're at home, you're sitting in something. If you're standing, whatever, it doesn't matter. Sitting, standing, walking, whatever you may be doing currently. Same logic will apply. Are there forces acting on you? None of you are, if we use our reference frame as this room, none of you are moving. So this just again helps us connect the ideas together. We're only going to go to 40 seconds here because this is hopefully very obvious. And from what I'm seeing on your responses, you're doing great. 5, 4, 3, 2, 1. All right, fantastic. Are there forces? Yeah, there's forces acting on you. Okay, why'd I ask this? It's so obvious. Why am I asking this? Notice I said forces. So if we look at Newton's second law, the one we just defined, we said that forces equal mass times acceleration. Now, I guess the follow-up question is, are you speeding up or slowing down? No, none of you are speeding. You're all, unless again you're online, you're walking around, whatever. None of you are, so your acceleration is actually 0. So if you plug that in here, that actually means the force is 0. But we just said there's forces acting on you. The net force is 0. The net force is 0. If you add up all the forces acting on you, they're 0. That does not mean that there's no forces acting on you. That means all of them combined are 0. And we're going to learn at some point later how to draw free body diagrams. The forces acting on you all right now are force of gravity. And we will learn later. Don't worry about this right now. But this is just giving you a little foreshadowing. Gravity pulls you down. None of y'all are falling. Why aren't you falling? Something must be pushing you up. And so this will also... when we see Newton's third law, will be good for us. Okay, so let's go ahead and do a math problem with this. Before I said we're getting Newton's third, we'll get to Newton's third law. We're almost there. Let's practice a problem with Newton's second law, one that lets us also utilize kinematics. So an 80-kilogram passenger in an SUV is traveling at 1 times 10 to the 2. That's just 100 kilometers per hour, and they're wearing a seatbelt. Good on them. The driver slams on the brake and the SUV stops in 45 meters. Find the force of the seatbelt on the passenger. First step, what's our givens? We've got mass, 80 kilograms. We've got the initial velocity. And if we really want to be fancy, we'll say in the x direction, just to get used to whole x and y and all that jazz. So the velocity initially, and we'll say they're going left, right kind of thing. 100 kilometers per hour. We will have to convert that to meters, so that's going to be 100 E3, and I'm going to have to divide that by 60 times 60, 60 minutes in an hour, 60 seconds in a... It's good to do this unit conversion, and we'll plug that into a calculator. I'm just converting this to meters per second. Everything's got to be in base units. These unit conversions, they are critical. All right, we get 27.78 meters per second, which again is fine. It helps us actually understand what's going on. I can't convert kilometers per hour, but if I remember that whole 23 meters per second is 60 miles per hour, they're going like 70 miles per hour in this car. All right. My change in X is 45 meters. And my final velocity is 0 meters per second. No unit conversions needed. 0 kilometers per hour is 0 meters per second. Everything's 0. Fantastic. All right. We are solving for the force. Okay. I want you all to spend a minute or two and think about how do we solve this problem. See if you all can kind of piece it out. What should I even do to solve this? I wrote down the givens. I wrote down what I'm solving for. What equations, given what information I have, how do I go from what I have to what I want? What equations will get me there? So think about it. Spend a minute or two. See if you can parse it out. Give y'all a hint. I'll give you one of the equations. This is in Newton's law, so we're probably going to use that Newton's law I just mentioned. Now, unfortunately, on the test, you won't really. So F net equals ma. And you look at that and you say, okay, great. I want F. I have M. I don't have A. So then your next thought should be, can I find A? And if so, how? These are the kind of logical steps your brain has to take to solve these problems. Whenever you're solving a problem, you don't process the entire problem in one go. It's in pieces. What's given? What's missing? And then you kind of start to process from there. Yeah.
Forces are going to be on the test?
Forces will be on the test. Yeah. Just to give you all a sense of organization-wise, problem set 1, everything in problem set 1 will be on test 1. Like, that's what will be on test 1 is problem set 1. Oh. Everything in problem set 2, that'll be for test 2. And then problem sets 1, 2, and 3, that's what the final will be on. So as far as organization-wise. Okay. So the next, we have to find A. So it's a kinematics problem. How do I find A? Okay, I've got delta x, I've got VFX, I've got VIX. It's going to be VF squared equals VI squared plus 2 delta x. You look through your kinematics equations. Once you realize kind of, okay, I need A, and there's a bunch of X's and B's, that's kinematics. Your mind should immediately go to kinematics. What equation has what I have and has what I need? That one. I need A. I have VF, I have VI, I have delta X. So I can rearrange this so that A equals VF squared minus VI squared all over 2 delta X. That's just some algebra there. I didn't do anything, just algebra'd it around. And then if we want to get real fancy, we could even plug that into here. But honestly, that's just a little bit extra writing. It's not worth it. We'll get the acceleration multiplied by mass and we'll be done. That'll be it. So, let's do it to it, y'all. So acceleration equals 0 minus 27.78 squared. Don't forget that squared. Those are always one of the most common things to forget, is to forget to square things. And we get an acceleration that is negative 8.57. That negative is important because I was moving in the positive direction. This person is braking. Remember, whenever you get an answer, you should think, does that make sense? I was moving. I come to a stop. If my velocity was positive, I have to have a negative acceleration to slow down. I'm slowing down when my velocity and acceleration are opposite signs. Okay, so that's good. We also have to think, is this a reasonable acceleration? Is this like actually realistic? Is this going to like kill the person? How do we have a sense for acceleration being reasonable? Gravity is negative 9.8. You all are okay experiencing gravity. This person is going to be okay experiencing this. This is a little bit less than gravity. So gravity is kind of your touchstone for what's reasonable. Yeah?
Other than gravity, what else could be reasonable in terms of G? Like how much kind of regular?
That's the easiest one to compare it to.
Okay.
Because if you, so 1G, most, you can jump off something and you're okay. Jump off like a little bit. As long as it's over time. What would be a very unreasonable is like 3 times G, or 3 Gs. So to give you all another sense, 3 Gs is about the max you'd experience on a roller coaster. That's like at the most extreme spot would be like 2 to 3 Gs. You're going above 3 Gs, you're going above like you're going above what you'd experience at a roller coaster. You get up to 10 Gs and you're black at like very dangerous. So 10 times 9.8 would be 980. Yeah. So yeah, good question. All right, and the last step is fairly F net equals M times A. So we're going to take this 80 and we're going to multiply it. We'll go ahead and keep the negative here because it's a vector as well. And we get an answer that is negative 685.6 newtons. Now, how do you decide if that's if the acceleration is reasonable? At the end of the day, the acceleration is the thing that actually matters. When you're trying to understand what someone's going to do, the acceleration they experience is actually the physical thing that's changing. I could have a force of 1,000,000 newtons acting on something, but that object has 100,000 kilograms. The acceleration is ultimately what matters, and that's actually what we're going to see in the next problem. So force is great, sure, super interesting. Whether or not this is a large or small force all depends upon the mass, which in turn means, how is my thing accelerating? Do I have a large acceleration or small acceleration? How do you figure that out? Divide by mass. I already did that. So there you go. Negative because it's pushing them backwards. It's slowing them down. The force would be opposite to the direction they're moving. Okay. So there you go. Nice little, you can expect to have to be able to evolve kinematics and forces together. That's the whole, they go together. Everything builds. All right, so the next question to y'all, finally getting into Newton's third law. I won't tell you what the law is yet. Some of you may know it already. A 2,000 kilogram truck runs into a fly. Which experiences a greater force? If you've ever taken a physics class before, this is a class. This example is always used. Maybe not. A car running into a fly. One of the most common ones. And no one ever likes the answer. All right, this is kind of a just guess situation, so we'll go to 45 seconds. It's one of those you know it or you don't. In 5, 4, 3, 2, 1. Okay. Again, this is one that everyone hates, but I hope by the end of this, as you all process this, all right, you're not going to like this. The force is the same. Again, a lot of you probably know that. Even if you already know that, you may not still like the answer. Because the logical thing, everyone always says, but the fly, but the truck doesn't even notice, and the fly does. So, Newton's third law, we'll see it in a second. is that for every force there's an equal and opposite. For every force there's an equal and opposite. And again, you're going to look to say, but the force is the same. Why does the fly get splattered and the truck does nothing? Let's go ahead. So force on the truck equals force on the fly. That's what it's just, that is Newton's third law. Whether you like it or not, that's how it works. Let's go ahead and quickly connect that to Newton's second law. Because remember, at the end of the day, you could have a huge force, but it's not the force that matters. It's the acceleration that matters. The acceleration is actually the thing that you all are used to seeing. How much does this thing speed up or slow down? So if we kind of put that in, the mass of a truck is 2,000 kilograms times whatever acceleration it experiences. That will equal the mass of a fly. I have no idea what the mass of a fly is, so I'm just going to make up a number. A paperclip is about 1 gram. A paperclip is about 1 gram. We're going to assume a fly weighs even less than that. So let's just go ahead and say a fly weighs like 0.1 grams. I really don't even know how much a fly weighs, but we're just going to say 0.0001, so 0.1 grams, which is this many kilograms. You know, maybe even smaller than that. And let's go ahead and compare the accelerations that they experience. The acceleration that the fly experiences, so this is truck, this is fly. The acceleration that the fly experiences is 2,000 divided by 0.0001. That's how much bigger it is than the acceleration of the truck. If you do that number, 2,000 divided by 0.0001, we get 2 to e to the 7, so that is, I got to count my zeros here, 1, 2, 3, 4, 5, 6, 7. So whatever acceleration the truck experiences, the fly experiences an acceleration 20 million times more. So this matches what your expectation of reality is. The acceleration. That fly went from moving, or not moving, who knows what the fly was doing, but guarantee you it's whatever it did change the second it hit that truck. It is now stuck to that truck. If it was not moving, now it's going 60 miles per hour instantly. That's a lot of acceleration. You would also be like the fly if you experienced an acceleration that high. Went from nothing to something instantaneously. Hence why, if you get by train, you are the fly now. You will go from nothing to something real quick. From 0 meters per second to whatever that train's doing. And same thing with a fly. So, when it comes to forces, and you're like trying to understand how much does a force affect something, really acceleration is the thing you have to think about. How much is it speeding up or slowing down? And this is how this example starts to actually make sense. When you picture it in accelerations, not forces. Because according to Newton's third law, this is an observation of reality. This is like, this is, out of all the things, this is just how things are. Whether you like it or not, if this is wrong, then everything's built on this. For every force, there's an equal and opposite force. The example I like to give, and when I teach my high schoolers this, my hand hurts by the end of the day. If I punch the wall, it hurts my hand. Why? I punch the wall punches back. That's why your hand hurts when you punch something. If you punch someone in the face, your hand's made of bones, their face is made of bones. If you break bones in their face, that same force is acting on your hands. That's why if you don't know, I have no idea how to punch someone in the face, by the way. But if you don't know, like me, and if I really wallop someone in the face, I guess there is a right way to do it. But if you don't know how to do it right, which again, I don't even know what the right way is, your finger bones can also break. Because if you're putting enough force in their face to break their face bones, your finger bones, their bones. So there you go. Equal and opposite force. My hand was moving, I hit the wall, it then went from moving to not moving. Something had to stop it. A force had to act on it. It accelerated. Negative acceleration, but that's an acceleration. So yeah, this is all over the place. Right now, none of you are falling. Gravity's pulling you down, but you ain't falling. Something's pushing you all back up. Your seat. Your seat is literally pushing back up on you. Another example is jumping. When you jump, no one is like trying to throw their foot into the air to jump. You push down, and yet you go up. I push down, the floor pushes up. I go up. At no point when you're jumping are you pushing up. You can't, like, you gotta push off something. You push down, the floor pushes up. There's so many examples of this. The other one that I do with my high schoolers, if I push on this desk with socks on, so I reduce my friction, if I push the desk to the right, I don't know how sturdy this is, we're just gonna hope my desk at school, I go backwards. I am not pushing backwards. I'm pushing to the left, I move to the right. Why? The desk is pushing back on me. For every single force that acts on anything, there is an equal and opposite. You push something, it pushes back the same amount. So, anyway, it's a really interesting one that has a lot of consequences to everything around you. So now anytime y'all think, when you are walking, you are literally pushing against the ground and you move the other direction. Yeah?
So how does this apply to the fly?
To the what?
How does this apply to the fly?
Yeah, so for every force there's an equal and opposite. So the car is going this way. Let's just pretend like the fly's not. There it is. The fly's not moving. The second that truck hits the fly, it pushes the fly. So at some point the fly hits this and the truck pushes the fly this way. The fly pushes the car the other way. Yeah. Yeah, but the acceleration is so small. The force is identical. If that force on the fly is 10 newtons, then the fly is pushing on the car with 10 newtons. Now, it's not that high. Again, if you think of F net equals m times a, it does not take much force to kill that fly. It does not take, and remember our examples, it does not take much force to accelerate a small object. It takes a lot more force to accelerate an object with a lot more mass. So it's really easy for that truck to make that fly move. It's really hard for that fly to make the truck move, even though the force is the same. Yeah?
Is it because when we're pushing something, it gives us the same force we're applying for the same reason the fly that we're applying?
Exactly the same reason. Yeah, if you push against a wall, it's a silly picture, but it does the job. If you push against the wall that way, the wall pushes back the exact opposite way. It's one of those rules in your every single force. This also applies to gravity. The earth is pulling you down. You are actually pulling the earth up. But your mass is so much smaller than the earth. Like we were saying, the mass of the fly was smaller than the truck. The mass of you compared to the earth, the mass of the earth is a number followed by 24 zeros, I believe. So yeah, you all don't accelerate the earth very much. In fact, one of the classic questions is if we gathered everyone on earth to one location, and would that affect things? No. The mass of the earth is so much beyond the mass of every single human being on it. We're like nothing compared to the size of the earth, for good or for bad. That's the reality. But you are pulling on the earth. It's just so tiny, it doesn't really change much. So, this does get all sorts, anyhow, we'll get to gravity at some point. But yeah, Newton's laws are really cool. They're really, really simple laws. I mean, if we just kind of go through them. First one, things keep doing what they're doing until a force acts on it. Second one, force, mass, and force equals mass times acceleration. And the third one, equal and opposite. And every single interaction can kind of be collapsed and explained by those. Yeah?
What if it isn't equal? Like what if I push something and it doesn't push back equally?
Yeah.
I push something and
it moves and you don't?
Yeah.
So the key to that, so notice when I pushed against this desk, I took my shoes off. The reason I took my shoes off is so that you could actually see me getting pushed back. Because the reality is, if you push on something, so let's take an example, let's show my picture here. This person will slide backwards. But the question is, okay, why don't you slide backwards when you push on stuff? Friction. You get pushed backwards, your feet want to move backwards, the force of friction actually pushes you forward. So what you're kind of doing, when you have that force of friction, you're kind of coupling yourself with the earth. You're kind of taking the earth and using that as your kind of push thing. If you're on ice, you will slide backwards. It will always be the same. And so it is always the same, but friction pushes you forward. Now, consequently, that means that you're pushing the earth back, but it's the earth or whatever you're standing on the planet. Yeah.
So let's say it's something super light.
Okay.
Let's say even if
just like pushing this, or like pushing my water bottle across the table.
Right, exactly.
It is still pushing back on me. If this floor had zero friction, I would actually move backwards. Even if it's this tiny. Now, it'd be very, very tiny, because the mass of me compared to the mass of this, I have way more mass than this water bottle currently does, but I would actually move backwards. Another example of this in space, they can experience this. If you're floating in space and you want to get around, you throw something. That is fundamentally how rockets work. How does a rocket move in space? You push hot gas one way, and hot gas is like the smallest particle, but if you make that gas move real quick and you move a lot of it, you go the other way. Fundamentally, you cannot move in space without pushing something away from you. Often rocket fuel and stuff like that. So any kind of propulsion in space requires you to push something the other way, so you experience the force the other way. So it's kind of, again, crazy consequence of this. And again, just shows how genius Isaac Newton is. Like this, there's so many things here that parts of it make sense, and other parts really challenge our concepts of how we understand the world. And he discovered all of this. There was no space, like I use space a lot because that's where there's no friction and no air resistance and no gravity. He discovered all this stuff without being in outer space, ever. I mean, he could look at the planetary bodies, and that certainly was a huge contributor to help with this stuff. But it's cool stuff. Yeah.
So if you're pushing the wall and you don't move, is it like the sum of like the friction, your force, and then the like negative of the wall pushing back, and then all equals 0?
Everything cancels out, yeah. So you push on the wall. Now, the funky thing is, if you're like in a building and you push on the wall, you're on the floor. So you're actually like, if you push on the wall and your feet are getting pushed backwards and the friction's pushing you forward, the whole building is one system. So if your feet are stuck to the floor and you push on the wall, nothing's going to happen because you're inside this like box, this whole system. You push on the wall, your feet push the other way, everything cancels out. If we kind of go outside instead and you push on the building and your feet are like in the grass or something like that, it's kind of as if you're pushing on the building, which has a ton of mass, and your feet are then pushing against the earth, which has a ton of mass. And yeah, you can get everything to cancel out. If nothing is speeding up or slowing down, all the forces cancel. It doesn't mean the forces don't exist. It just means they cancel out. Just like you all right now, gravity's pulling you down, and yet you are not moving because it's pushing you back up. Forces are still there. They're exactly equal and opposite, but they cancel. Yeah. So if you are not accelerating, it doesn't mean there's no forces. It just means they cancel. Yeah. And this stuff gets kind of complex when you start trying to understand what the system is. So the word system is going to come into play in physics a lot. The system is everything that's interacting together. So, again, when I'm wearing my shoes and I push on something, the floor actually contributes because of the friction. That becomes part of it. Whereas if I somehow make it slipperier such that the floor doesn't affect it, then it doesn't. So this stuff gets complex. You have to think about a lot of moving pieces, and you have to think about all the pieces that are interacting. Now, I say that mathematically it's not going to be terrible. And next week is all about us just finding forces and how they interact with each other and all that kind of stuff. Actually doing the math of this stuff. And we'll talk about free body diagrams, but next week is kind of applying this and calculating net force and acceleration and all that jazz mathematically. So, all right. We already talked about this, but this will see. So I kind of got ahead of myself, but it's good to know that current me and past me had similar ways of thinking. So we already answered this, but yeah, the forces are the same, but the acceleration is not. And ultimately, the acceleration is the reason why. The acceleration is what's actually happening. This whole forces thing, you can only measure forces indirectly. Kind of a weird idea. It's an interesting kind of, I don't know if homework is the right word for you all. An interesting thought exercise for you all. Measuring position, very straightforward. You get a meter stick or something. You can measure distance, position, all that jazz. Measuring time, that's an interesting one. But, fairly straightforward. You all got clocks on your phone, you can measure time. How do you actually measure force is an interesting thing that you all can kind of think about. How do you even measure this stuff? You can think of a scale. How does a scale tell you your weight? That is a force. How does it even work? Something fun for y'all to kind of look into.
Is the question asking which experiences like a greater change in acceleration? Or
Yeah. No, a greater acceleration is actually fine. I mean, they're both true. A greater change in acceleration. At the point of impact, they will both accelerate. Which will accelerate more? Yeah. In the beginning, neither one's accelerating. Presumably, at the end, at the point of impact, they are both experiencing acceleration. All right, we'll go to 5, 4, 3, 2, 1. Again, this really was an exercise and who's paying attention? Yeah, the fly. The fly accelerates more. That's why it dies. There's the show The Expanse has a really good example of this happening to a human. In The Expanse, they're flying real fast in a spaceship, and the person goes from like super fast to nothing like that, and they look like a fly in a winch. Yeah, they just get absolutely. So, yeah, if you experience a high acceleration, you will be the fly. Yeah.
This is an example of like a 100-kilogram tree.
Yeah.
Would you go to how like far a tree one?
The ratio would be the ratio of their masses. Yeah. So if you have a 100-kilogram tree, 2,000 divided by 100, it would experience 1/20th the acceleration that the car would. Now, that gets a little tricky because the tree has roots, and those roots are in the ground, and so those roots then, like, how much of the roots holding on? So if instead we said a 2,000-kilogram truck and a parked car that had, like, that would be a bit better. Even then, there's friction involved, which complicates things. But yeah, that's a good point. Yeah.
So, how can you make F net not equal 0? Because, like, I feel like it's just always going to be 0, even if it...
That's a good question. How do you make F net not equal 0? So, like, if I throw a water bottle, I'm kind of, again, because of friction, I'm not going to accelerate. Really, because the mass of the earth is so giant, like I'm coupled with the earth effectively with this. So if I toss this thing, yeah, the water bottle pushes against my hand, but this will fly forward. And honestly, the net force of every system is 0. But at the end of the day, we only care about forces because we care how things accelerate. So this will accelerate, even though the net force of the whole system is 0, and therefore we looked at the whole system, the water bottle, me, the earth. That whole system, the acceleration would be 0 if we kind of got it all together. But we focus just on what the water bottle's doing. We don't worry about me, we don't worry about the earth. Because if I say I toss this water bottle, how far will it go if I toss it with a certain force? At the end of the day, I care about the water bottle only, and so we just look at that. Even though the whole system is 0, the force in the water bottle is not. Just the water bottle. So, again, that's kind of funky, but you have to choose what you're looking at. Yeah.
So it's equal.
Yeah, the net force in the entire universe of everything happening is 0. If we took the entire universe. But that's, when we look at specific problems, we focus in on one piece of the universe. Yeah, so it's a good question. I like that. All right, so free body diagrams. This is kind of the last thing I need to teach you all. And this picture, actually, I'm going to kind of scribble over this orb with white. Because what I want to show you all, so when we're solving these problems, and if we want to figure out, this is not the most elegant solution, I'll go back and fix this. If we are solving a problem, we have to figure out all the forces acting on that one object. And so to that end, something we're going to do is draw a free body diagram. To be honest, I do not know where that word free body comes from. I've heard it so many times, now that I'm teaching to you all, it's the first time I'm pausing and thinking, why is it called that? It's a diagram. It's going to show forces. Why is it called that? I don't know. That's a fun thing maybe for me to look up in my free time. But here's what's important to you. Every one of these will begin by drawing the object. And this is where it's going to test your art skills. You're going to see my art skills real quick. Behold, as I show you my picture, if I wanted to find the force on this water bottle, behold my drawing capabilities. There's my water bottle. That's what a water bottle looks like in physics in a free body diagram. If you want to draw the force, the free body diagram, if you on the chairs, here's my, I'm going to pick Eric here in the front. Here's Eric. There he is, looks just like him.
Yeah, exactly.
There's gravity, and there's the chair pushing up. If I want to draw that force on the car, hitting the fly, all right, there's the force of the car. You know, the fly is going to push the car a little bit backwards. Here's my fly. It gets accelerated forwards. Every free body diagram is basically just a box, and you draw your arrows starting from the center of it. That's going to be how we're going to draw these, and we're going to get a lot of practice with this over the next week. Free body diagrams, anytime you have a problem with forces, this is the first step you will do. Remember, the first step we do in every problem is draw a picture of it. This is how we're going to represent our forces. So we will draw the object and we will say what forces are acting on it, in what direction, and all of those forces will emanate from the center of it, just because it makes it easier for us to keep track of them all. You'll see as you practice this notation is for our own benefit. It's not because I'm doing it because it's busy work. It's because it helps us organize the information. It helps us see what's going on. For example, right here, I drew a free body diagram of you all sitting in the chair. Ideally, if I did a better job of this, FG and FN would be the exact same size, and you can see they would cancel out. The acceleration is 0. Fantastic. If instead I drew a free body diagram of you sitting in the chair and I drew it like this, again, don't worry what FN right now necessarily is, just worry that it's a force. It's the force of the chair on your butt. If I drew that, that is an inaccurate picture, because according to this picture, FN, the force of the chair on your butt, is bigger than the force of gravity. So by extension, you all should be accelerating upwards right now. You are not. So again, these pictures help us kind of see what's going on. And, shock and awe, X and Y are separate from each other. When we do the math, these are vectors. We will have to split things into the X component and the Y component. So, just get ready for that. Alright, so there you go. Again, this is a ball. I personally like ball. Pick whatever you want, y'all. Like, I told you a box. If you instead want to draw my water bottle as a sphere, if you instead want to draw Eric as a sphere, feel free. It really doesn't matter what shape you draw. You want to make it a smiley face? A box is just what I was taught. If you want a circle and you like circles, whatever. If you actually want to draw the picture, it makes you feel better to draw it, go for it. But at the end of the day, you draw something and you draw the forces acting on it. So here's a kind of a silly example. There's a dog, bunch of dogs pulling a teddy bear. They're each pulling that in their respective directions. And so, no, I don't expect you to draw a teddy bear with a bunch of dogs around it. Here's the teddy bear. Again, that or your box. Pick your poison. Doesn't really matter. And then we just draw the forces. We do not draw what the forces are caused. We label them. You know, we'll call this dog 1, dog 2, dog 3. We label our forces. It's just a way to organize information, y'all. That's what pictures are there for. It's just one of the quirks of being human. We do good with visual information. It's helpful for us. Why? That's psychology. But trust me, it's helpful. You'll see for yourself. At some point, it'll just become second nature for you all, that when you're starting a problem to draw a picture, give it time if it's not already. Okay, so a telephone pole has 3 cables pulling. F1 is 300 I hat plus 500 J hat newtons. F2 is negative 200 I hat newtons. And F3 is negative 800 J hat newtons. Find the net force on the telephone pole in component form. Find the magnitude and direction of this net force. This is a useful problem. So, at some point, a lot of y'all will have to take statics. Statics is all about things not moving, the net force being 0. Your buildings should have a net force of 0. You generally do not want to be in a building that's accelerating. We will discover if this telephone pole, is accelerating or not based on this. So, first step, before I even write anything down, free body diagram. I'm going to draw these vectors. That first vector is 300 in the I hat direction and 500 in the J hat direction. You have some options here on how to draw this. What I'm going to do is I'm going to go like 300 over. You get to decide how much 300 is. Just once you set it, it is what it is. And then I'm going to go 500 up. 500 is bigger than 300. Didn't give myself enough room, so let's just make 300 a little bit smaller. All right, so that's my F1. It goes up 500, and it goes over 300. Newtons for both of those, but that's kind of assumed. All right, and thank goodness the way these other ones work out, they're not going to get my way. All right, F2, is negative 200 I hat. That's in the x direction. It's a little bit smaller than my 300, but I'm going to make my box a little smaller. Boop, 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 boop. All right. There we go. That's F2. I made it a little bit smaller than 300 because it's 200 newtons that way. I could even put that here. F2 equals 200. Now, notice, I didn't put the negative there because I have it in the picture. If you want, I guess, sure, we'll put the negative there. Why not? That's fine. That may be helpful to us later. All right, and F3 is negative 800. And to be honest, y'all, I'm being super careful with my picture here, trying to make sure my arrows are really accurate. For you all, as long as you know whether they're bigger than each other or smaller than each other, that's the extent. You don't need to get like your ruler out and make sure it's super accurate. The more accurate your picture, the more useful it is for you. But at some point, is it worth the time and energy? You just need to know whether they're bigger. F3 is 800 is bigger than 500. It's good for me to show that this is bigger than that one. So you want to get a sense of things with your picture. All right, so, the givens. Sure. F1 equals 300 I hat plus 500 J hat F2. At this point, I've already kind of written them down. If I was solving this problem, just me, I would not bother writing them again, honestly, here, but just to show you all as thorough as possible. Find the net force. F net equals add up all your forces. So I'm going to use a little bit of a weird notation here. That's sigma, capital sigma. Add them all up. Now, you have to remember. So sure, I wrote this, but the reality is I need to get all my forces in the x. I need to get all my forces in the y. If you are working with vectors, it does not matter what vector it is. If you are working with vectors, you have to break them into x and y components. If it's three-dimensional, x, y, and z. You cannot combine vectors without breaking them into x and y. That is just something, that's like a rule that you all have to get used to, because you're going to learn about lots of vectors in this class, in physics 2, in your future engineering classes, and all of them follow this rule. Yeah?
What about if they're in the same direction?
If they're already in the same direction, that's a great point. So sometimes you get lucky. Sometimes you get lucky, and for example, we'll have a force that's going up to the right and a force going down to the left. In that case, they're already lined up with each other, and so you can do that. But those are kind of special cases, and you'll kind of discover this as go on. At the end of the day, why do we break them in x and y? We can only add vectors that are parallel and anti-parallel, is the logic. So if they happen to be parallel and anti-parallel already due to just convenience, sometimes you get lucky like that, and you don't have to break an x and y. But you have to ultimately know you're adding parallel and anti-parallel. Yeah, that's a great question. Okay. So, real quick, y'all, let's just knock this out and be done with it. So, step 4, add them up. F net in the x is going to be 300 plus negative 200. It's always adding. Adding a negative is subtraction, but I think it's good to get in the habit that summing them, it's always adding. Right is positive, left is negative. And down, up is positive, down is negative. F net in the y, we can use our little picture here. Again, this is the cool thing with pictures, y'all. It makes your life so much easier to kind of see why I've added those. And the net result we get is, I should have given myself more room, that the F net in the x will be 100. So F net x equals 100 newtons. So that's 100 newtons to the right. That's a positive value. And the F net in the y is negative 300 newtons. So my F net total is going to be 100 I hat plus negative 300 J hat newtons. You want to get the magnitude, a squared plus b squared equals c squared. You want to get the direction, tangent inverse. So this one's to the right and down. If you want the angle, there it is. So that's 100, that's 300. There you go. The last step I'll leave for you all. Let me double, triple check. Yeah, maybe we'll look at a couple of these things. Next week we'll get more into force, doing more calculations, but that's a really, we did it. We got caught up, basically. Next week we'll be able to basically start the next PowerPoints on forces. The extra two things here, and maybe we'll worth it. Good luck, y'all, with 2D kinematics. Take your time. Make certain you know 2D kinematics, projectile motion. That's kind of the trickiest problems we've done so far. Make certain you know what you're doing with those. Take your time. Work together. Do it to it. Put in the time and the energy.
Have a good weekend, Doc.